Okay, so I think it's time. And today I'm showing the first slide that I showed when we started the school, and a view of the Mont Blanc, which we should have seen had the event taken place live. This is the final session. So there will be a morning session now, and then this afternoon, Harold Huang will give the final presentation for this Les Houches school. And I would like to take this opportunity, especially for our attendants from Asia, to thank you all for being present, at least virtually present, to this school, despite the fact that we were not able to hold it live. We definitely hope that this format, although unusual, suited your expectations, and having your feedback is of great importance. So please send us emails. You can send it to the secretary of Les Houches, saying what you thought of this school, and making suggestions, which will be very helpful for forthcoming events. Even though I would rather prefer that these events happen live and not virtually. Anyway, so now I will pass.
Mark.
Yeah.
Mark, just before, I think we should all thank you for all the work you've been putting in the school. So on behalf of everyone, thank you very much.
Well, thank you.
Yes, thank you.
It was really a pleasure to organize it. And I mean, I received help. I mean, I didn't do it all by myself. The secretaries did contribute effectively, even though you didn't see what they did, but they put up quite a bit of work into it as well. And it was very useful to have the input of the co-organizers. Okay, so this being said, a co-organizer will be the moderator of this morning session. So Ralph, I will pass the baton to you. Here we go. Okay.
Well,
okay.
Just before he starts, I would like to do some cheering for you.
Thank you.
Yeah, Mark, cheers also for me. Thank you very much for the great job that you have done. Yeah, good morning, everyone. So this is the last day, as Mark just pointed out, after 3 weeks of intense learning about emergent electronic states and interfaces. I have enjoyed this very much. I learned a lot myself, and I have understood what this is all about, what interesting quantum states you can generate, what materials you need for them, what techniques we have to investigate them. But now that we have already proceeded very far in our understanding, we can think also about controlling these states in a little bit more refined way. And this is something that we will hear about today by Andrea Caviglia. He will show us how you can use light for manipulating and controlling quantum states at interfaces of materials. Andrea took his first degree at the University of Genova in Italy, and then began his PhD project with Jean-Marc Triscone in Geneva, just changing one letter in the university name, I noticed. He took his PhD in 2010 and worked on already oxide heterostructures there. And then he spent 2 years as postdoc at the Center for Free Electron Laser Sources in the Max Planck Institute for Structural Dynamics in Hamburg to learn about what you can do with high-intensity light sources, and took up his present post as professor at the Caviglia Institute of Nanoscience at the Delft Technical University in 2013 to work on designer quantum materials. Andrea, please tell us about your great work.
Thank you, Ralph, for the kind introduction. And thanks very much to all the organizers, Mark, Jean-Marc, Ralph, and everybody else for this kind opportunity to contribute to this beautiful school. So today I would like to tell you about interfaces of quantum materials, how we can think of controlling their properties, both statically and dynamically using light. But before I go deep into the science, let me thank and mention the big players in this activity that I will discuss today. So I will be talking about the PhDs and postdoc projects of Thierry Fantil, Dima Afanasiev, Jorik Tortensius, and Dirk Groenendijk. And I would like to mention many great collaborations with both theorists and experimentalists. On the theory side, we have a lot of great support from Mario Cuoco and Silvia Picozzi's groups in Italy. We have had very nice experimental collaborations with the group of Jean-Marc Triscon, especially with Jennifer Fowley and Stefan Varillo, that I will talk about today. We benefit from a lot of great TM work from Nicolas Gauquelin. And I would also like to mention the great theory collaboration with Eric Bousquet in Liège and with Marc Habert in Paris. And before I go into my talk, I would like also to spend a few seconds advertising some open positions that we have in our department. So our department is called Quantum Nanoscience. It's located at the Kaffer Institute of Nanoscience in Delft. And we currently have open positions for faculty in the areas of quantum matter, quantum sensing, and quantum transduction. So if you're thinking about starting your group, please consider Delft. It's really a great place where we have a fantastic infrastructure, great students around, and overall a great place to do research. Okay, so let's start with the question, why should we be interested in quantum physics at interfaces? So, and especially at interfaces of quantum materials. So if we look a little bit back in the past, we can immediately see that many beautiful discoveries have been made at interfaces of semiconductors. For example, if you take gallium arsenide, aluminium gallium arsenide heterostructures, you can discover topological phenomena such as the integer and fractional quantum Hall effect. And these discoveries made with high mobility electrons have made tremendous societal impact with technologically important steps forward, such as high mobility field effect transistors, and now the building blocks of quantum information, qubits, and etc. So all these fascinating properties came out of the study of interfaces of semiconductors, so systems that in the bulk are characterized by independent electrons. So a relatively simple quantum physics that gives rise to many new phenomena when you look at interfaces. Now, the next step for this field is to be interested in interfaces of quantum materials. So now you start from systems that already in the bulk have very interesting properties. So you start, rather than having independent electrons, you have interacting electrons. And your system can be characterized by broken symmetries, topological states, and collective excitations in the bulk. And now when you're looking at interfaces, you can perceive immediately that some rich new physics can emerge. And the question is, what are the key differences between interfaces of semiconductors and of quantum materials? And let's highlight one important difference. So when you look at interfaces of semiconductors, you are basically thinking of quantum confinement through band engineering. So you can design your, for example, aluminium gallium arsenide stackings with an appropriate difference between band edges, such as you can define a quantum well both for electrons and holes. Now, if you're very smart and you inject electrons inside this quantum well in the appropriate way, namely using modulation doping, so separating donors from the charge carriers, you can realize highly mobile deconfined electron systems in 2 dimensions. So here you have broad envelopes for your wave functions of the order of tens or hundreds of nanometer, very low densities of electrons that can propagate at extreme mobilities and give rise to a lot of interesting physics. Now, if we look at interfaces of quantum materials, we have a radically different picture. So these ideas of band engineering still have some merit in this context, but they don't tell the whole story. The whole story is more rich. So now we have quantum mechanical interactions that vary on atomically sharp scales, So here I'm representing an interface between material A and material B that are characterized by different microscopic parameters. So the on-site Coulomb repulsion, a hopping integral, a magnetic interaction, a spin-orbit interaction. And when these two materials meet at the interface, you have a atomically sharp modulation of this microscopic properties. Additionally, it is becoming more and more clear that geometric phases also play an important role in the system. So you have geometric objects such as a Barry curvature that vary from one material to the next, and you can think of modulating a band topology at the interface. So here you have a new laboratory where you can play with the interplay with an interplay of electronic correlations and band topologies to create new states of matter. And the new frontier also for this type of studies is to consider the many-body physics of the system out of equilibrium. So to stimulate the system with intense laser fields that carry tens of mega electron volt per centimeter electric fields. So they are able to perturb significantly the properties of the interface. And think of these parameters now as some time-dependent objects. So break time inverse symmetry in this new way. So thinking of driven system out of equilibrium. So these are the subjects that I would like to talk about. But you have many rich ingredients here, but from many ingredients you don't necessarily have a good meal. So it is important to think carefully about what kind of combination of parameters that you modulate in an interface, and try to have some rationale on this type of studies. And for example, let's consider the interplay between the Coulomb repulsion, the hopping integral, and the spin-orbit coupling. So if we visualize these parameters on a phase diagram, we can distinguish regions of the phase diagram in which you have weak correlations, and a region in which you have strong correlations. So this has been intensely studied in the past. And now a region where you have weak spin-orbit coupling and strong spin-orbit coupling. And from the last decades of research, it is apparent that when you have weak correlations and weak spin-orbit coupling, you have your system that can be described as simple metals or Fermi liquids, or band insulators. But as you crank up the strength of your electronic correlations, you can have a transition towards a multi-insulating state. This has been a very important field of research for decades. More recently, it has become clear that when you crank up the intensity of spin-orbit coupling in materials, you can enter into a region of topological phases of matter. So you start to have special edge states that appear in your materials. And now with these systems of interfaces, we can think of exploring this special region of the phase diagram in which you have both strong electronic correlations and possibly topological properties. And one example are the spin-orbit multi-insulators that have been intensely studied in the past decade or so. So the focus here is to thinking of a smart way of manipulating these microscopic parameters. So electronic correlations, spin-orbit coupling, band topology, in order to design and produce new electronic phases at these interfaces. And I'm going to give you some examples this morning. So I will start by discussing interfaces involving iridate materials. So where we stack spin-orbit multi-insulators of semi-metals, and I will show you that these materials can be controlled through a correlated phase transitions by their dimensionality. And I will highlight the important role of the coupling of structural instabilities between different materials. So we are stacking together materials with different symmetries, different crystal symmetries, and this has profound consequences on their electronic properties. Then I will move on to discuss the manipulation of geometric properties of these materials, and I will show you that if you play with the interfaces of an itinerant ferromagnet, from some Ruthenate, you can manipulate its Barry curvature, which is a source of emergent electron dynamics, and therefore you can define the anomalous transport properties of these systems at interface. And finally, depending on how much time I have left, I would like to address the questions of the states out of equilibrium. And I would like to give you an example of a surface phenomenon in which you can derive an out of equilibrium ferromagnetic phase by making the atoms of your system oscillate very fast and very intensely. Okay, so this is more or less the outline, the various topics that I would like to cover. We will go from discussing static control of these interfaces towards the most cutting edge, let's say, at least for our lab, of dynamic controls using resonant phonal excitations. And before I enter into the individual project, I would like to broaden a little bit the scope and discuss a little bit some fundamental properties of the perovskite materials that will be useful for the discussion. So the material focus here of this talk is on perovskite type of materials. So these systems realize a cubic symmetry that incorporates both a system of BO6 octahedra, where B is a transition metal and O is oxygen, and a lattice of A-site cations. So in the high temperature phase, we find a cubic symmetry. And the beauty of this perovskite structure is that it allows you to incorporate a great variety of transition metals. And depending on the transition metals that you incorporate, you can find a broad spectrum of electronic states. So just in our lab, we study things from diluted superconductors to various magnetic systems to multi-insulators by changing the type of transition metal cations that you incorporate in the structure. And then associated with these ground states, you find very elementary excitations that are exciting to study. And everything is tied together by strong structure property relations. And what is the magic? Why the perovskite structure allows you to incorporate so many different cations, so many different types of transition metals in the system? I mean, the key element is that the perovskite is able to accommodate many different cations thanks to many structural instabilities that it can have that lower the symmetry of the crystal and allow you to put in cations with large different sizes. But in order to realize an ideal cubic structure, for geometrical considerations, you need to have the bond length of the A to oxygen cation to be the square root of 2 of the bond length of the B and oxygen. So that's for the ideal case. If you now try to incorporate in the structure a cation that is too small to realize this geometric arrangement, then the system can tolerate this by executing polar or antipolar motions of the B cations. And this is a situation that you often find in ferroelectric type of materials. If instead you put in a cation that is too small to realize the cubic symmetry, then the system has an instability to create anti-polar motion or polar motion of the A atom these times. And this is also accompanied by oxygen octahedral rotations from antiferrodistorted modes. So the key aspect that the perovskite system is very tolerant to accommodate many types of cations with the price to pay of realizing various structural distortions. And it is useful to classify these structural distortions according to the Glaser notation. So we focus here on the patterns of oxygen octahedral rotations that are realized in these materials. And if you look at the literature, you essentially see that you have 3 types of symmetries that are realized often at low temperatures. Either a tetragonal phase, a rhombohedral phase, or an orthorhombic phase. And these are characterized by either no rotations of oxygen octahedra or in-phase rotations of oxygen octahedra or out-of-phase rotations of oxygen octahedra along a specific axis. Then you can indicate these as using this Glaser rotation. By X, you indicate the axis of rotation, and 0 plus or minus indicates no rotation, in-phase rotation, or out-of-phase rotations. And the subgroup relationships determine what types of phase transition are symmetry allowed when you cool your system from a high symmetry cubic phase down to a lower temperature, a lower symmetry phase. And as I said before, the most common type of transitions are those that bring you either to this rhombohedral A minus, A minus, A minus pattern. So that's typical of systems such as lanthanum aluminate, and LSAT and things like that. We have this pattern of rotations, or the orthorhombic systems are very common. We have a PNMA type of symmetry, and A minus, A minus, C plus type of rotations, or tetragonal systems. So, for example, the case of strontium titanate that is very often studied is a A0 C minus type of distortion, where you have out of phase type of rotations along one axis. Okay, and when you now create interfaces between materials that have all these symmetry lowering properties, then you have the problems of realizing a connectivity between the oxygen network. So if you, for example, here I'm depicting a simple schematic case of a tetragonal or cubic system that meets a more distorted perovskite system. And as you can see at the interface, you need to resolve the connectivity of the oxygen network. And one possibility that you have is to create a leaking of distortions between the two materials. So here you immediately see that the interfacial region of where these two materials meet is strongly structurally reconstructed. So you have a interplay between electronic reconstruction that brings in new orbital physics and a structural reconstruction. So you can have stabilization of polar or antipolar modes, which involve electric dipole order, which may strongly influence your electron system at these interfaces. You can change oxygen rotations, which may influence spin counting and therefore being active on the magnetic phase transitions and metal to insulator phase transitions by renormalizing the hopping. You may be touching upon the anterior distortions, which will influence spin and orbital order, or breathing modes, such as in the nickelates, where you have a checkerboard pattern of small and large oxygen octahedra that you're touching upon the charge order of this system. So by playing with this various structural and electronic degrees of freedom, you can both statically and dynamically control your interfacial properties. And I will start by discussing some examples of the static control. So the first subject is the control of spin orbit multi-insulators by the dimensionality and the coupling of structural instabilities in iridate type of materials. So why looking at iridates? So iridate materials are quite fascinating in themselves already in the bulk, because they realize a very strong entanglement of orbital and spin degrees of freedom. So iridium in a 4+ state is characterized by a D5, 5D5 electronic configuration. So you have 5 electrons in this 5D manifold, which is split by the cubic crystal field already to form a T2G occupied manifold. Now, if you consider spin-orbit coupling in this context, you realize that spin-orbit coupling is so strong that it leaves the orbital angular momentum partially unquenched. So effectively in this system, the orbital angular momentum can be described as an effective orbital angular momentum 1, which summing up with the spin 1/2 of the electron forms the J effective 1/2 state and 3.5 states. So the 3.5 states are lower energy, and the J effective 1/2 state is at higher energy where the chemical potential lies. So this band can be fairly narrow in certain systems, and therefore you can have a multi-instability. So if you add Coulomb correlations in the system, you can split the electronic structure into a lower Haber band and an upper Haber band, and realize a system that goes from a metal to an insulator. So importantly, these J effective 1/2 electronic states are a entanglement of orbital and spins, where you involve different orbitals and different spins in the superposition. And I would like to stress the fact that in this superposition you have an imaginary component. So this spin orbit driven mixing causes your system to have a quantum phase that is very important for the physical consequence, because as you know from your basic quantum mechanics, if you have wave functions that are characterized by a superposition of a real or an imaginary part, then when you are performing adiabatic evolution in configuration space, in addition to the usual trivial phase factor, the dynamical phase factor, you will also pick up a geometric phase factor or a Berry phase. So the presence of this inherent quantum phase causes your system to acquire a Berry phase, a finite Berry phase during adiabatic evolutions, and this can give rise to topological phenomena in these materials. So these iridates are a good place where we find both Coulomb repulsions and the possibilities of topological behavior. So they're worth investigating for at their interfaces. And if you already look in the bulk, we see that these materials can go through a dimensionality controlled metal to insulator transition. So in the two-dimensional limit, where you realize the strontium 2 iridium oxygen 4 phase, you have a fairly decoupled two-dimensional iridium oxide plane with a narrow band, and these systems undergo a multi-instability, and so they show a correlated multi-insulating ground state that is also antiferromagnetic with an in-plane magnetic moment in a strong counting of the spins, which is caused by this unusual J effective 1/2 physics. So it's remarkable that the spin counting is exactly equal to the octahedral rotation angle. When you instead go to the 3 to 7 phase, you still have a multi-insulator, but now the spins, they point out of plane, so they form a collinear antiferromagnetic state. And if you go to the three-dimensional limit of the 113 strontium iridate phase, you find a semi-metal that shows paramagnetic behavior in the bulk. And so in a sense, using these bulk materials, you can already navigate this phase diagram in which you vary the strength of U over T, so the relevance of correlation with respect to the bandwidth of the materials, and you can navigate this MOT transition. Now, the question that we asked ourselves a few years ago was, can we explore this type of phase diagrams now using the film thickness as a control parameter? So can we essentially go from the 113 bulk phase down to a two-dimensional limit and trigger a transition towards a correlated insulating state with some magnetic properties. So that was our initial goal, and it was a bumpy road. And the difficulty is that the iridate materials are extremely complex to grow. So they are materials that since you're dealing with a very large B cation, it is hard to obtain films with a correct stoichiometry of the system. And it's very hard also to prepare a target that is able to support a PLD growth process correctly and that contains the correct stoichiometry. So this was also a strong collaboration with chemists that help us to synthesize a target with an appropriate iridium stoichiometry. But after a lot of work, we succeeded in obtaining very high quality strontium iridate thin films. So using these particular conditions, you can have very sustained read oscillations during the growth of these systems. And as I will explain later, we always cap our film also with an epitaxial layer of strontium titanate to essentially protect these films. And these films are coherently strained to the substrate in a compressive strained state. So this is a TM of one of these iridate heterostructures with the strontium titanate and a capping layer of strontium titanate again. And you can see that we can indeed fabricate pretty good films. The transport properties of this semi-metal, this paramagnetic semi-metal system are quite unusual. So this is a resistance versus temperature curve of a 30 unit cell film. And you see that you have a anomalous temperature evolution with an exponent of the order 1. So this may be interpreted as a sign of correlated behavior of these electrons. And we also observe a very sharp kink in the resistivity at 105 Kelvin, where there is a transition of the crystal structure of the substrate. I will come back to this point later on in my presentation. I was telling you that we always cap our films with strontium titanate, and this is very important if you want to perform systematic studies as a function of thickness of these systems, because these films tend to degrade dramatically when exposed to ambient conditions. The strontium iridate, if you leave them on these films in ambient conditions over time, they will turn insulating, and you will see that a lot of chemistry is going on the surface with interaction of your films with the humidity in the environment. If you instead cap your system with an epitaxial strontium titanate, your system is stable over time and can be processed in the clean room to realize transport devices. So we systematically study different thicknesses, and we are able to fabricate whole bar devices. See, there is a question from Ralph. Am I allowed to take questions from chat? Is that okay?
Just take a question.
Yeah. So there's a question on the iridate layer itself is conducting, or is it an interface effect like with the layer? Right. So in the bulk, the strontium iridate is a paramagnetic metal. So in itself, in the bulk, the system is already conducting. And I will show you that as you create interface with strontium titanate, you can modify this system. Yeah. Okay. All right. So thanks to all this material science and clean room work, we were able to study systematically the variation of transport properties as a function of thickness, and the result is reported here. Essentially, films that have a thickness larger than 4 unit cell show a semi-metallic behavior at all temperatures, and films that have a thickness of 3 unit cell and below, they show a sharp transition towards a strongly localized behavior. Already in the high temperature range, the sheet resistance of the system is of the order of the quantum of resistance, 25 kilo. So already in a strong localization sense, it is expected that these films will undergo a localization of the wave function. So the question is there any role played by electronic correlations in this meta-tensoriator transition? And I will argue that electronic correlations are indeed important, and I will show you one theoretical and 2 experimental evidences for this. So on the theoretical side, we collaborated with a group of Bicozzi at CNR Spin, very strongly with Altieri. They performed a lot of DFT studies in this system, and he was able to show very systematically that as a function of thickness, strontium titanate, strontium iridate heterostructure display a meta-tensoriator transition. And in order to observe this transition, it is fundamental to have a U of at least 1.5 electron volt, and it's important to allow for the system to have both structural distortions and antiferromagnetic order. So antiferromagnetic order is essential in order to stabilize the insulating phase. Without antiferromagnetic order at a DFT level, the system remains a metal. The density of state that is observed at the Fermi level is quite interesting. So you have a superposition of J effective 1/2 and 3.5 character of the bands, and the coexistence of both electron and hole bands. And we studied very systematically the electronic structure for thick films, where we everything was consistent with this picture. In the study, we combined high field magnetotransport at 31 Tesla, thermoelectric measurements, and field effect. And the picture is the picture of a semi-metallic state with a very balanced electron hole contribution, where the product of the densities and mobilities of the carriers are essentially equal. So a very interesting semi-metallic state of this. And in the thin limit, an important role of electronic correlations in stabilizing an insulating state. And the next step that we took experimentally was to look at the local density of states using STM and STS, so scanning tunneling spectroscopy. So in order to perform these studies, we built a vacuum suitcase in order to transport our films from a PLD chamber to a very nice STM that is available in our department for this type of study without breaking vacuum. So this was the master project of Lucinda Kutstra, and many others improved the system afterwards. And so we have a transfer system that is based on a Omicron sample plate, so we can manipulate the sample from the POD to the STM chamber without breaking vacuum and transport it with a battery operated pump in between. So this is very important because, as I told you before, the iridates degrade in air dramatically, so we cannot afford to expose these thin films in air during the transport from POD to STM. And so through this effort, we were able to measure the local density of states of our thin films as a function of thickness. And so the result is shown here. And what is important to see here is that we systematically observe as a function of thickness a reduction in the density of states around the Fermi energy, with a particular V shape of the other density of states. So this type of behavior is reminiscent of a pseudo gap, as observed in most lightly doped multi-insulators. In the strontium iridate 214 itself, this phenomenon is observed. So here is a work of the group of Milan Allan by Irene Battisti, where they studied scanning tunnel spectroscopy of lightly doped strontium iridate, where they introduced lanthanum dopants, and there they showed exactly the same type of V-shaped reduction of the density of states at the mode transition. So we believe that this indicates that a similar type of correlated transition is occurring as we reduce the thickness at 4 and 3 units out in this thing. So the second experimental evidence that something interesting is happening at this crossover is the evolution that we observe of inelastic scattering times by magnetotransport measurements. So we measure systematically across this phase transition the magnetoconductance of this iridate thin films, going up to 10 Tesla. We were able to observe a transition from weak localization for thin films on the verge of the transition to weak anti-localization for thicker films. So this is in a sense expected as we are localizing our charge carriers, and it's an indication that the spin orbit scattering time is changing as a function of thickness, as well as the inelastic scattering time, and everything can be estimated through weak anti-localization fits of the magnetoconductance. The new phenomenon that is observed here, that is different also from LAO STO interfaces, if you're familiar with the field, is that the dephasing length of the system estimated by these fits has a very strong evolution as a function of thickness. So this is not the case, for example, in LAO STO. So as we go below the 10 unit cell limit, we observe a very sharp variation of the dephasing length. And as you know, the dephasing length is something that gives us information on the magnetic susceptibility of the system. So this indicates that there is really a strong enhancement of the magnetic susceptibility of the system as we approach this insulating state. So a strong enhancement of spin fluctuations is observed by magnetotransfer. So this is consistent with the DFT results, that in order to stabilize the insulating phase, you do need this spin ordering to occur. So as the system starts to form patches of antiferromagnetic order domains, you start to enhance your spin fluctuations. In parallel with our study, also the Würzburg group from our chairman Ralph Claessen was also interested in this problem, and they have provided beautiful for photoemission data that is published here, where they directly saw the transition from a conducting state to a correlated insulating state by mapping the whole Fermi surface of the system. And this is very nicely consistent with our transport data and our magnetotransport. Okay, so this brings me to my first partial summary of this first project. So I showed you that with the interfaces of strontium iridate, you can change the dimensionality of strontium iridate going towards the two-dimensional limit, and engineer a correlated insulating state. So this occurs, the gap opening at 3 unit cell of strontium iridate with a pseudo gap behavior observed at 4 unit cell. And in this regime, the system crosses over from being weakly localized to have weak anti-localization with a strong enhancement of spin fluctuations. Okay, now let's go back to this kink in resistivity that I showed you before. So I showed you that in this semi-metallic state, the thin films of iridates on top of strontium titanate display a very anomalous behavior at 105 Kelvin. If you measure 5, 4, and 6 unit cell films, you can always detect a very sharp kink occurring at 105 Kelvin, which corresponds to a transition from a cubic to a tetragonal phase of strontium titanate. So what's going on here? A second interesting transport phenomenon that is observed is a very strong transport anisotropy that occurs at the structural phase transition. So if you fabricate a transport device made, for example, as a van der Pol type of square, where you have your contact current and voltage probes at the edges of the square, you can inject your current and detect voltages in different directions in your sample. You can switch your current and voltage probes systematically across this type of structure. And then you can orient your current in different directions with respect to the tetragonal domains that you observe in your sample. So this is an optical microscopy image of one of our devices. So, and by using polarizers in your microscope, you're able to resolve these 45 degrees domains oriented at 45 degrees with respect to the 100 and the 010 crystal axis of strontium titanate. If you do so, you see something very interesting, that when you go below this transition, so when these domains form, your system behaves as a semi-metal along one direction and behaves as an insulator along a different directions. So what is the cause of this anisotropy? What temperature is this picture? It's measured at 4K. Thanks, Thierry, also for answering. Yeah. Thierry is actually the person that made the measurement. So this is done in a cryostat that has optical axis. Yeah. So your system looks like an insulator when your current is going a certain direction, and as a metal in the 45 degree direction. So there's something interesting going on. And so in order to understand this point, we need to look at the various lattice instabilities of these two materials. So strontium titanate has this transition from cubic to tetragonal, which is described by a A0, A0, C minus pattern of rotations. So you have one rotational axis along which you have out of phase rotations. And when you go through this phase transition, your lattice will break up into domains. So the domains will be characterized by the direction of the rotational axis. So either along the A, C, or B lattice parameters. The A0, C minus A0, and C minus A0, A0 domains are obviously oriented at 45 degrees with respect to the 110 and 010 axis. The lattice instability of strontium iridate instead is quite different. So instead of a tetragonal system here, we have an orthorhombic symmetry. So orthorhombic means that you have A minus, B plus, C minus pattern of rotation. So one axis of rotation will have in phase rotation, while the other ones will be out of phase. So when you have an in-plane lattice matching with the strontium titanate, this will produce only 3 possible type of structural domains. So you can either have A minus, A plus, C minus, or A plus, A minus, C minus. So in principle, all these are allowed, and the question is, do they all occur? So we wanted to really understand how this octahedral network couple across the interface, and how we can rationalize the influence that they have on the electronic properties. So in order to address these questions, we went to diamond light source And we teamed up with the group of Jean-Martin School in Geneva, especially with the help of Jennifer Fowley and Stefano Garillo. And we went to measure essentially the doubling of the unit cell of these materials that is triggered by this pattern of oxygen rotation below the phase transition. So when you go from a straight octahedral network to a pattern of tilt of the octahedral network, you immediately see that your unit cell is being doubled along a certain direction. Therefore, you want to measure half order Bragg peaks that will directly see these rotations in place. And we were very surprised to see that essentially the in-phase rotational axis for these films always lies in the plane of the interface. So the main result of our synchrotron experiment is that one type of domain is completely absent in our films. So the A-, C+ domains are not present in our films at all. So these will be domains in which the axis of the in-phase rotations points out of the plane of the interface. And these type of domains are completely absent in our films. Instead, we only find films where the in-phase axis of rotation lies on the plane of the interface. And this is consistent with our DFT calculations performed by Carmine Altieri, where he finds that having the in-phase axis of rotation oriented out of plane, so out of the plane of the interface, is always energetically more costly, of several millielectron volt. So the system always favors having a in-phase axis of rotation on the plane of the interface. So now we can answer the first question of how does the octahedral network couple? So essentially the A-, A+, C- and the A+, A-, C- domains in SIO, they couple directly to the C-, A0 domains and the A0, C-, A0 domains of STO. So that there's a direct coupling of one type of tetragonal domains in the STO with one type of orthorhombic domains in the SIO. So two lattice instabilities across the interface have been directly coupled. So STO is providing really a template along which the orthorhombic domains of strontium iridate can arrange themselves. And now the second question is, how does this influence the electronic properties of the materials? Well, DFT calculations indicate something very interesting. So you start from a semi-metallic state where you have a mixing of J effective 1/2 and 3.5 electrons and holes. And this creates a situation in which you're very sensitive to the distortion that you have in the system. And the result is that along the out of phase axis of rotations, your wave function will experience a larger hopping parameters. While along the in phase axis of rotation, your wave function will experience a smaller hopping parameter. So this explains naturally our experimental observations. So the kink in the R versus T is caused by a sudden change in current distribution that occurs at 105 Kelvin at the moment in which the orthorhombic domains of strontium iridate lock to the tetragonal domains of strontium tetrate, with this special 45 degrees domains. And the anisotropy is explained by the fact that now we have this template in which along one direction, along the out of phase axis of rotation, we have a larger hopping parameter. So we have an easy transport axis along the direction, which is characterized by semi-metallic behavior. While along the in-phase axis of rotation, DFT tells us that we have a smaller hopping parameter. So that's a hard transport axis, and that favors carrier localization in the system. So we have a very interesting loss of symmetry in the system. So you go from a system that was symmetric with respect to in-plane rotations to now having a highly anisotropic character. Okay, so this brings me to my second partial summary. So I've shown you that at these strontium iridate strontium titanate interfaces, you can have a coupling of structural instabilities across the the interfaces, and the strontium titanate domain structure is really providing a template for the domains of strontium iridate and dictating a transport and anisotropy in the system. This is very interesting to explore for nanoscale transport phenomena. So now we really have an interesting playground in which we can define this current path that in principle should also be associated with antiferromagnetic order in the insulating directions. All right, and now I would like to switch to the third example of control of electronic phases at oxide interfaces by discussing the engineering of topological transport, so of Berry phases in an itinerant ferromagnet strontium Ruthenate. So strontium Ruthenate is another interesting candidate for topological phenomena. So in this case, ruthenium in a 4+ configuration has 4 4D electrodes, and in this material, the tetragonal crystal field creates a different splitting from the previous case. So this is characterized by this energy scale delta, and you have this part of your electronic structure that is mainly characterized by, so all the orbitals are mixed, but here you are mainly of the XY character, while in this section of the manifold you are mainly the YZ and the XZ character. And when you again spin orbit split this structure, you create an entanglement of orbital and spin degrees of freedom. So it's not as strong as in the iridates to create a J-effective state, but still it is strong enough to create a strong entanglement of spin and orbitals with, again, an inherent quantum phase. So the consideration that I made above on the generation of Berry phases in the system through adiabatic transport is still relevant. So these Ruthenates are systems in which Berry phases can be acquired. And this has been extensively discussed in the literature. So strontium Ruthenate in the 3-dimensional limit is characterized by Weyl points. So these Weyl points occur when you have this crossing of spin split band structures that produce an avoided level crossing through spin-orbit coupling. So here you have a mixing as illustrated here, and these special points are sources of Berry curvature, of anomalous Hall conductivity, and interesting spin dynamics. This has been studied. So this is a proposal that came already in 2003. And here in this particular paper, the topological structure that was discussed for strontium Ruthenate in the bulk was essentially a single source of Berry curvature at the gamma point that was dubbed here as a magnetic monopole. And this was used to understand the evolution in magnetization and temperature of the anomalous Hall effect in this system. So the Ruthenate display a very unusual change from a positive to a negative anomalous Hall effect that finds its explanation in this band topology. So how can the anomalous Hall effect arise from a Berry phase? So everything arises from an additional term in your electron dynamics that is called the anomalous velocity. That is present whenever your system has either time or an inversion symmetry broken. So this term is characterized by this quantity called the Berry connection, and its rotational is the Berry curvature. And the Berry connection is basically acquired during an adiabatic evolution of a Bloch wave packet that occurs whenever your system is under a constant electric field. So when you apply a DC electric field, you can represent this as a constant vector potential that increases monotonically with time. So this causes an evolution of a Bloch wave packet around configuration space, and each component will acquire a different Berry phase whenever the time or inversion symmetry are broken. So the resulting phase differences will sum up to give a certain Berry connection, which will be a source of the presence of effective electromagnetic fields in your system. And the minimal model to characterize this type of behavior was discussed in this paper. So here you are considering a Zeeman split system with spin-orbit coupling, in which there is an avoided a level repulsion here around the gamma point. And a sign change of the Barry curvature and therefore of the anomalous Hall effect is described by the theory that includes both this type of electronic structure and impurity scattering. And one example of observation of this type of behavior is this beautiful experiment by Kei Takahashi in 2009, where they took ferromagnetic europium titanate, and here they control the sign of the anomalous Hall effect by systematically varying the band filling. So as you move your Fermi level across this special point, which is a source of your Barry curvature, you can turn your anomalous Hall effect from being positive to being negative. So the question that we ask ourselves is, how does this vial point evolve when we reduce strontium Ruthenate from the three-dimensional limit to the two-dimensional limit? So that was question number one. And then can we use this insight to manipulate the Barry curvature at the interfaces? And in order to answer these questions, we teamed up with a group of Mario Cuoco that performed effective Hamiltonian calculations of strontium Ruthenate in the two-dimensional limit, supported by DFT calculation. So the novelty of the calculations of Mario and colleagues was that they included in their effective Hamiltonian both spin-orbit coupling and next nearest neighbors interorbital hopping. And this has allowed us to show that the system actually possesses topologically non-trivial bands in the two-dimensional limit. So this vial system, when that is present in 3 dimensions, when you go to 2D, it displays 2 topologically non-trivial bands with Chern numbers +2 and -2. So these are prevalent DYZ and DXZ orbitals, and the DXY orbitals instead are topologically trivial. And at the Fermi level, there is a point in which through spin-orbit coupling, there is an unavoided level of crossings. So this is a point that is a source of Barry curvature, which is represented in this graph here. So you have various poles in momentum space that can contribute either negatively or positively to your Barry curvature. And the balance between these various sources will determine whether you will have a global anomalous Hall transport that has a positive sign or a negative sign. Okay, so that's the key aspect. And also very important is the fact that these level crossings occur between topologically non-trivial bands. So these are robust against variations of electron occupations. So no matter where your Fermi level is located, and depending on impurities, you will still have these topological points. And the relative occupation will depend whether you will observe in a transfer experiment either a positive or a negative Barry curvature. And importantly, now if you think of this system in the two-dimensional limit and you put an interface, so interfacing these materials with other systems, you will be able to influence these topological points and control the sign of your Barry curvature. And this was demonstrated theoretically by our collaborator, Cuoco, Altieri, Brzezinski, which were able to show that when you interface strontium Ruthenate with a titanium oxide, you will observe a prevalent negative sign of the Barry curvature, while when you interface strontium Ruthenate with strontium Iridate, you will observe a prevalent positive sign of the anomalous Hall effect. So having these theoretical predictions, we aimed at observing this type of phenomena. So we asked ourselves, can we manipulate the Barry curvature of strontium Ruthenate by interfacing it with either strontium titanate or strontium Iridate in symmetric types of heterostructures. And so we synthesized this type of raw materials. Again, the excellent work of Dirk Groenendahl and Thierry Fantil in making these samples, this very difficult synthesis possible. And we benefited also by a lot of TM characterization of Nicolas Gauquelin. But the insight from TM is that the interfaces are very sharp, except the top interface, strontium Ruthenate, strontium Iridate, that has an intermixing over 1 or 2 units out of iridium and ruthenium. And the bottom line is that the prediction of quark and collaborators is actually verified in experiments. So if we measure films of strontium ruthenate, it's anomalous Hall effect at low temperature, when it's sandwiched only by strontium titanate, you observe a negative sign of the anomalous Hall effect, a negative Barry curvature. Well, if you have a strontium ruthenate film of the exactly same thickness now embedded between strontium iridate, the sign of the anomalous Hall effect is positive. So you can indeed manipulate the Barry curvature. This is not an accidental temperature at which this occurs. So this is the sign of the anomalous Hall effect as a function of temperature, measured for strontium titanate, strontium ruthenate, strontium titanate, and strontium iridate, strontium ruthenate, strontium iridate at between 1.5 Kelvin and 250. And you see that this negative sign and this positive sign is observed very systematically across all temperatures. And this is a direct indication that we have manipulated a topological structure in momentum space. So we went from a set of prevalent multiples of Barry curvature that had a positive contribution to a prevalent set of poles that gave a negative contribution. This type of observation of a topological nodal structure was also verified very recently in an archive paper that came out of the Seoul group, whereby photoemission spectroscopy, they were able to see this exact nodal structure that we proposed since 2018. Okay, so now a good question is, what do you do with this? So now you have a technique to manipulate the anomalous Hall effect in these atomically sharp interfaces. And one thing that you can do is you can make some spintronic devices. So one useful spintronic device is called the extraordinary Hall balance. So that's a device that functions as a memory device with 4 states. So it's a device in which you stack 2 magnetic layers with different switching fields, and possibly also with different sign of the anomalous Hall effect that allows you to distinguish between different states as a function of magnetic field. So in order to realize this type of spintronic device, we fabricated heterostructures that incorporate 4-unit cell of strontium ruthenate, 4-unit cell of strontium titanate, and 5-unit cell of strontium ruthenate. So here you have strontium ruthenate layers that are decoupled by an insulating barrier. So there is no charge transfer across this barrier. We have a question. How from photoemission they could get the Barry curvature? Yes, good question. So from photoemission you measure the avoided level crossings, and from the avoided level crossings, then you can calculate the associated Barry curvature. But I agree with you. In photoemission, you don't measure directly the Barry curvature. Actually, Barry curvature is proportional to the off-diagonal component of the resistivity tensor. So that's a transport measurement is a more direct measurement of this phenomenon. Let's say this is the whole thing is nicely consistent though. Okay, so the same tuning of the Barry curvature that I discussed with the strontium iridate interfaces can also be observed by changing the thickness of the layer. So from going from 4-unit cell to 5-unit cell, you can manipulate this sign change of the Barry curvature of strontium ruthenate. And if you create such a stacking, then you have a device in which you combine 2 transport channels that have different switching fields, and they have different signs of the anomalous Hall effect, and this can realize this interesting devices in which you can switch your state of the anomalous Hall transport through 4 possible states, depending on the various arrangement and of spins and signs of the anomalous Hall effect in your system. So this is the data that we acquire at different temperatures, in which you realize different configurations of your spin arrangement, and these are the fits of this data using this particular arrangement for the channels as a fitting parameter. Okay. So you might be tempted when you see something like this to think of the topological Hall effect, but we believe that this effect can also be explained by band topology. I discussed now the possibility of using geometric phases as a tool to control spin and charge accumulation and peroxide interfaces. And in my view, this is an interesting way in the future to explore the interplay of topology and electronic correlations in condensed matter systems. Okay. Ralph, can I ask you how much time I have left?
Formally, you have 15 minutes or 17 minutes left, but you answered already a few questions, so I can grant you another 5, say 20 minutes.
Okay, but 15 should be fine for me to wrap up with the light phenomenon. Okay. So just to wrap up this part, so I showed you that when you thin down strontium Ruthenate, the system starts to exhibit spin polarized topologically non-trivial bands that show anti-crossings in momentum space and sources of Berry curvature. And this can be manipulated at interfaces, and you can use this to realize spintronic devices. Now, in the last part of my talk, I would like to mention a little bit the possibility of dynamical control of the electronic properties of oxides. The idea is that when you have systems of electrons that act collectively, then associated with this collective behavior, there are collective excitations. So in a magnetic system, you will find magnons. In a superconductor, you will find superfluid excitations, and in general, you will always find phonon modes in these crystals. And in the Mott-Hubbard systems, you will find special type of excitons. So if we can, so many of these low energy modes, they carry an electric dipole. So it is possible to couple light directly to this type of excitation and bring the system out of equilibrium to generate states of matter that you could not access through a thermodynamic transformation. So this realizes the idea of dynamical control of materials. And this is an old research field, and typically people have been exploring hidden states of matter, so accessing some high energy metastable configuration in your configuration space by exciting your system with pulses of laser light. Yes, I will come back to this question at the end if it's okay. So yes, you can also change the Berry curvature by changing the number of SRO layer. Then that's also a control parameter. Yeah, I went a bit fast on that. I will come back to that in the questions. Okay, so this is the idea of switching. Another idea is to induce dynamical stability. So if now you couple your radiation with low energy modes of the system that define the ground state, it is possible to directly change the profile of your configuration potential of the system, and therefore render a state metastable and favor phase transitions towards a competing state of matter. So a driven system, in principle, has access to new type of ground state that are generated by dynamical stability. And the way we try to pursue this type of experiments is by coupling short pulses of laser light in resonance with phonon modes. So we want to perform the most gentle perturbation we can to the system while still being effective. And so the idea is to create pulses of light in the mid-infrared range that are tuned in resonance with phonon modes of the material, displace atoms out of their equilibrium position to a large extent, and cause a rearrangement of the electronic degrees of freedom in the system. And in order to perform these experiments effectively, you need to ask yourself, what kind of electric fields do I need? And in a solid, you typically have electric fields of the order of hundreds of megavolt per centimeter. So these are the typical interatomic electric fields. And in a simple laser pointer, you have electric fields of the order of 100 volt per centimeter. So a laser pointer will not do much to, even if it's tuned to a particular resonance, it will not do particular atomic displacements. So you want to generate electric fields of this orders of magnitude. So, and in order to do so, in Delft, we have worked very hard, and especially Dima Afanasyev has been a big player in this effort in building a special laser source that is fed by a short 100 femtosecond 5 millijoule pulse at 800 nanometer. So this is the output of a titanium sapphire laser, and this system has a series of optical parametric amplifiers that are seeded by the same white light and difference frequency generation that eventually produce a pulse that we can control in its wavelength between 6 and 18 microns, and carry an electric field of the order of 10 megavolt per centimeter. So a significant fraction of the electric fields that you have in matter. And so note that we pay a large price in order to produce this field. So the energy efficiency here is not great. So we start from 5 millijoule per pulse here, and we get 5 microjoule per pulse at the end. But still, this is enough to produce electric fields that are significant and can displace atoms out of their equilibrium positions. So why do we need them to be strong? So we want to dynamically induce lattice distortions. And if your the amplitude of your electric field is low, then you will only reach a harmonic response regime. So you will induce some oscillations around the equilibrium positions of atoms that will rapidly decay. And this will not have profound consequences on the electronic properties of your material. Instead, if your electric field has a significant amplitude to touch upon the anharmonicity of your crystal lattice, then you can have the phenomenon of rectification of your phonon field, and then you can generate lattice distortions. So the key here is to displace ions enough from with large enough amplitude to be able to experience an anharmonic response of the lattice. And I want to show you that this is indeed the case with a simple case of lanthanum aluminate. So as I showed you before, lanthanum aluminate has a A- rhombohedral distortion at 800 Kelvin with a condensation of 2 modes. So even at room temperature, it is a crystal that has some anharmonic behavior. So we have a mode that goes from being stable to being unstable as a function of temperature, and this is associated with lattice anharmonicities. So how do you see that you displace atom out of their equilibrium position? So this is a very important measurement performed by Iridates Hortensius. So it's the reflectivity of lanthanum aluminate as a function of time. And here Iridates is exciting the lanthanum aluminate with either an off resonant laser pulse, so that it does not couple in resonance with the phonon mode of lanthanum aluminate, or in resonance with lanthanum aluminate. And you see that when you're off resonant, you don't induce any oscillatory response of your reflectivity. While when you couple your incident light in resonance with an infrared active phonon mode, so a aluminium oxygen breathing mode of the system, then you observe a large oscillations of the reflectivity with a spectrum centered around 1.1 terahertz. So this is a oxygen octahedral rotation mode. So it's a Raman active mode that has been excited through nonlinear coupling between the phonon modes. So by exciting a phonon mode at 20 terahertz, you have induced a rotation at 1.1 terahertz of your oxygen octahedra. So through nonlinear phonon-phonon coupling. As I told you before, it's very important to be able to access these oxygen octahedral rotations, because these govern a lot of interesting electronic properties of our materials. So this is what we are aiming to do here, to control on very fast time scales these structural modes of the material and to induce transformation in the electronic properties. In addition to this Raman mode activation, when we excite the crystal lattice of lanthanum aluminate, we also observe the generation of ultrafast strain. So we observe this again by measuring reflectivity and polarization rotations of a light probe. And if you do so, you see a pattern of oscillations occurring in the gigahertz range. So this pattern of oscillations, they correspond to the propagation of a sound wave across your crystal. And the oscillations are a pattern of destructive and constructive interference of the probe pulse that is either reflected from the pristine surface of your material or by the propagating strain wave. And importantly, we observe in our experiment both the propagation of a transversal strain wave and a longitudinal strain wave. A longitudinal strain wave is fairly expected to occur in this type of experiment, simply by the fact that you have a strong electrorestrictive response of your material. So when it's exposed to large electric fields, your lattice will change. But the generation of a transverse strain wave is quite peculiar. It's quite special, and we find it very fascinating because a transverse strain wave is a B over A type of change in your lattice parameter. So it's a shear strain. So by changing the photon energy of our excitation pulse, we can tune the response from being purely a longitudinal acoustic strain wave to being mostly a transverse strain wave. And a transversal strain can be an interesting tool to manipulate the properties, the magnetic properties of materials, especially in kind of a system with multiple Ora parameters. Okay, so when you excite resonantly the lattice using strong laser pulses, then you have three phenomena. You have the generation of low energy modes in of the Raman type, which involve coherent rotations of auction octahedra. And in addition, you have generation of strain waves that are propagating across your material. So what can you do with that? One thing that you can do is that you can take your lanthanum aluminate, you can grow on top an epitaxial layer of neodymium nickelate. You can excite this interesting structural dynamics that I just described in the lanthanum aluminate and observe how the neodymium nickelate film will react. So this neodymium nickelate is an antiferromagnetic insulating system at low temperature. And if you do this type of excitation of the crystal lattice of lanthanum aluminate, you observe that the antiferromagnetic order in the films rapidly melt with the propagation of a wave inside the antiferromagnetic materials. So there is a supersonic melting front that propagates in the film. So at speed that are much faster than the speed of sound. So that's one application. The other application that I would like to discuss more in detail is the actual control of magnetic phases. So instead of melting a magnetic phase, the switching of an antiferromagnetic material to a ferromagnetic behavior driven by this type of physics. And the idea is again to rely on spin-orbit coupling. So we know that in this type of spin-orbit coupled magnets, the magnetization is locked to the lattice by spin-orbit coupling. So if you, with your laser, introduce some particular pattern of change in your lattice structure, you can induce a change in magnetic anisotropy, and therefore a reorientation of your magnetization. So this is the idea, and this is relevant for the problem of magnetic recording. So when you want to switch a magnet from an up state to a down state, you need to overcome a certain energy barrier, and the size of this energy barrier is not set by the exchange interaction, but rather it's set by the magnetic anisotropy. That's what defines our energy barrier. And typically this is done in ferromagnets by exciting spin precessions. So by exciting precessions of the spins, you can kick this ball across the energy barrier and switch from positive to negative. So these are coherent spin precessions that are typically induced in microwave experiments. And the precession frequency reflects the local curvature of the magnetic potential. If these precessions have a sufficiently large amplitude, you will be able to overcome the energy barrier and to go from one state to the next. In our experiment, we aimed not at overcoming the energy barrier, in a sense, but to manipulate the energy barrier itself. So the question that we asked ourselves is, can we manipulate the magnetic anisotropy on the ultrafast time scales in order to lower the energy barrier, induce some coherent spin precessions, and an easy transition from one spin state to a competing one. And I want to show you that this is indeed the case, that if you excite resonant large amplitude lattice vibrations, you can modify the magnetic energy landscape sufficiently to allow for magnetic switching to occur. And the material that we use for this study is the rare earth orthoferrite, dysprosium orthoferrite. So this is an orthorhombic system where magnetism comes from ion 3+. And in the low temperature phase, you have an antiferromagnetic collinear arrangement. This is below the Morin point located in the bulk at 51 Kelvin. And in the high temperature phase, you have a weak ferromagnetic phase in which you have spin canting and a net magnetization. So this is called the Morin transition or spin reorientation transition. And it's a first order type of transition that occurs around 50 Kelvin. So with an energy barrier of the order of a few millielectron volt. And as being a first order phase transition is characterized by a competition between two energy minimum, one corresponding to a collinear antiferromagnetic arrangement and one a non-collinear weak ferromagnetic arrangement. So by changing the temperature, you can favor one phase versus the other. What we wanted to do in our experiment was to sit at a specific temperature, manipulate the crystal lattice on very fast timescales in order to change the magnetic potential and favor one phase over the other. So control a switching from an antiferromagnetic phase to a ferromagnetic phase via manipulation of the crystal lattice. And the key aspect here is to be able to measure the shape of the magnetic potential. And this is done typically by exciting spin precession. So if you excite spin precession, you will measure some frequency of oscillations of your magnets. And this will reflect the local curvature of your magnetic potential. So we do this by a pump probe scheme. So where we probe the Faraday rotation. So we send a probe pulse that has a controlled polarization of light. We measure the rotations of this polarization in the presence of a magnetic field. And by doing so, we are able to resolve the magnetization of the ion 3+ in this system. And this is a function of time delay between a pump and a probe. And the pump is tailored to either excite or not in resonance the lattice modes. So when we are non-resonant with the lattice mode with our pump, so we're not exciting the crystal lattice here, we are only exciting Raman processes, we can indeed activate spin precessions and measure an oscillation frequency of our spins, which well corresponds to the Raman spectroscopy of this material. And the surprise comes when you excite in resonance with the Fuller modes of the material. You indeed again excite a spin precession, but now with a highly renormalized frequency. So the frequency of this oscillation is being redshifted to a larger extent. So this indicates directly that by exciting the lattice, you are softening the magnetic potential. So you are changing the magnetic interactions in the system. A similar phenomenon, so this is observed in the low temperature antiferromagnetic phase. In the high temperature ferromagnetic phase, a similar phenomenon is observed. If you excite your system at resonance, you observe also a change in the magnetic potential, but this time instead of softening, it hardens. So the frequency of your spin waves is increased. So here you see the whole set of data of the magnon frequency as a function of pump wavelength, where you see the blue shift, so a hardening of the magnetic potential in the weak ferromagnetic phase, and the softening of the potential, so a red shift in the low temperature antiferromagnetic phase. So we can measure also how fast these changes in magnetic potential are activated and relaxed. And we can set an upper limit of a few picoseconds for the settling of this new magnetic potential, and up to hundreds of picoseconds for the relaxation of the magnetic potential to occur. What is the physical origin for the weak ferromagnetic phase to the antiferromagnetic phase transition? Yeah, good question. So as far as I know, there is no structural change associated with this transition, but there's an activation of the Yaroshinsky-Moriya interaction. So that across with the reorientation of your spins, you activate a Yaroshinsky-Moriya interaction, which causes the canting of your spins. And associated with this transition, there's also a change in the orbital occupation, in the thermal occupation of the dysprosium manifold. So you have this 4f electrons in the dysprosium that are being changed in the multiplet as a function of temperature. So that is believed to be the cause of the transition. Okay, so by measuring spin precessions in and out of equilibrium in our system, we are able to resolve the actual shape of our magnetic potential, and we can directly see that by exciting our system in the antiferromagnetic phase, we can create a metastable state where the antiferromagnetic state is not anymore the absolute minimum of the system. So the question is, can we excite the system with a large enough amplitude that the system can switch from this metastable state induced out of equilibrium to the ferromagnetic phase, so the weak ferromagnetic phase. And so in order to answer this question, we measured spin dynamics at different fluents of our excitation. And we see that for low excitation fluencies, the system remains in the antiferromagnetic phase and displays some harmonic spin dynamics that decay rapidly. But as we crank up the power of our excitation source, then we see that the system starts to develop a finite magnetization that grows and grows with time, and indicates the development of a net magnetization of our system. So this is a process that has a threshold of the order of a few milliwatt that you need to utilize in order to induce a large enough spin precession to drive the system from one phase to the competing one. And interestingly, this spin precession causes the switching to occur within the first half of spin precession frequency. So a truly ultrafast switching from the antiferromagnetic phase to the weak ferromagnetic phase. Yes. So the Yaroshinsky-Moriya so we have a question: is it the Yaroshinsky-Moriya interaction mentioned originated from lattice and spin-orbit coupling? Yes, the Yaroshinsky-Moriya is indeed present in our system, and it is relevant in the antiferromagnetic phase. Okay, so this data indicates that we indeed have a nonlinear spin dynamics with switching from the antiferromagnetic phase to the weak ferromagnetic phase. This type of transition can also be induced by charge excitation. So this has been demonstrated in the past, but there is a key difference. So when you excite a charge excitation in order to activate this Moriya transition, you're relying on heating of your electron system and then subsequent development of magnetization. So you see, this is this green curve shown here. So this is spin dynamics induced by a charge transfer excitation, and you see that you can induce coherent precessions of your spins up to a certain point where you start to see a magnetization developing. So overall, it takes about 100 picoseconds for your magnetization to develop when you excite the electronic degrees of freedom. Instead, when you excite the structural degrees of freedom, so you're resonant with a phonon pumping, then your magnetization itself develops within the first precession of your spins. So within a few picoseconds, you have developed your magnetization. So an improvement of several, 2 orders of magnitude in the speed of your phase transition. This highlights the more efficient character of photon pumping with respect to conventional charge excitations. What is the lattice doing across this phase transition? So we do measure second harmonic generation as a probe of the crystal lattice dynamics, and we do observe structural dynamics associated with this transition, which indicate that a Raman mode mixed with a strain wave is present in our system. So consistently with the lantern illuminate data that I showed you before. Okay, so that's my final summary. So by exciting on the ultrafast timescales the lattice at surfaces, at interfaces of these transition metal oxides, you can induce long-lived modifications of their magnetic interactions and drive spin reorientation phase transitions between competing magnetic phases. And this brings me to my conclusion. So that the perspective is to bring all these activities together and to look at electronic and magnetic reconstructions, both statically and on the ultrafast timescales using resonant photon excitation. And let me thank again all the people that have been collaborating for this scientific work. And thank you all for your attention.
Okay, thank you very much. I give you some applause
Thank you.
for this broad and fascinating overview. We already had some questions. Maybe we can start the discussion round by you completing your response to Yong Ah Su's question.
Yes. So we had a question on the let's say let's go back and the Barry phase aspects. Yeah, so here I went a little bit fast, but essentially this transition from a positive to a negative sign of the Hall effect also depends on the thickness of the strontium Ruthenate layer. So you can switch this transition to occur from higher temperature to lower temperatures. So by doing so, you can create a temperature range in which one layer of strontium Ruthenate has a negative sign of the anomalous Hall effect, and one layer of Ruthenate has a positive sign of the anomalous Hall effect. And this realizes this extraordinary Hall balance configuration, in which you have four possible accessible states in your system.
Mm-hmm.
Okay, so try to understand what you said. So you're saying that transition from a negative to positive signs on the film thickness, and so then you can have a situation where one of them is positive and one of them is negative. One thickness is positive, one is negative. Now, what happens if you have a thickness in homogeneity? So would you have a situation completely cancel? And then what happens in the infinite thickness, like in the 3D?
Yeah, that's a very good question. So when you have a thickness in homogeneities, what I think is happening is that you have both contribution. You have both a positive contribution to the anomalous Hall effect and a negative contribution. And these are spatially inhomogeneously distributed in your sample. So probably you will have a pattern along step edges in which you have maybe a larger thickness and a smaller thickness next. So this creates a situation in which this extraordinary Hall balance behavior is observed in a single inhomogeneous film. So this type of behavior in your Hall effect, in which you see peaks next to the switching points, can be observed also in an inhomogeneous thin film of strontium Ruthenate. And I believe this scenario has been discussed in a paper from the group of No. It's a nanolectors, I believe.
Young, you had a second question or another question on the light-driven magnetic transition?
Yeah. What was it?
Did you try the opposite transition from?
There it is. Did you try the opposite transition from weak ferromagnetic to anti-ferromagnetic fiber? Right. Okay, so now you're asking me about a possible transition from the high temperature phase to the low temperature phase. Okay, so this we haven't done yet. We would like to achieve this, but obviously it's a more difficult type of transition to access. So now you're asking, can we lower the symmetry of the system by exciting the lattice? Okay, and this requires a more clever, let's say, excitation scheme.
Mm-hmm.
Yeah, it's something that we are experimenting with ideas to achieve this, but it's not done yet.
Jean-Marc, you have a question on the iridates.
Yes. Yes, thank you. And Andrea, thank you very much. Beautiful results and beautiful talk.
Okay.
Yeah, a question on the iridates. When you look at the properties while reducing the thickness, you see that strontium iridate is turning insulating, and you showed photoemission data, I think from Ralph, and STM. Now, from the photoemission, it seems that the system is really nicely metallic and goes to an insulating state, opening a gap.
Yeah.
From the STM, it's a behavior which is a bit different. You have a V-shaped dip already in the metallic state, and somehow this dip is extending to lower energy and reaching zero. So I was just wondering whether you understand this behavior or these differences.
Yeah. So okay, the short answer is we don't fully understand this spectrum, but the key aspect is for samples with let's say 5-6 unit cell and above, we have a finite density of states at zero energy. So at zero energy, we always have some finite density of states. And at 4, we have really a full V-shaped going to zero just at 0. And then below that, we have a gapped system. And the same phenomenology is seen in strontium iridate 214, where you put a lanthanum dopants and you go and do spectroscopy in the vicinity of the dopants. In the vicinity of the dopants, you see the same V-shaped gap. And the title of this paper is like a universality of pseudo gap in a lightly doped multi-insulator. And I think the point that they're trying to make here is that this type of V-shaped pseudo gaps is something that you have in the vicinity of these transitions. Because this type of V-shaped was also used to claim D-wave superconductivity in this system. So there's some discussion there.
And Andrea, the value, okay, now I don't have the slide of on photoemission in my head, but the value of the gap is similar?
Yeah, it is. Yeah, this is the data from Ralph.
Okay, so it's much larger, the gap in photoemission.
Yes.
Yeah.
Well, it depends on which thickness you compare to, right? The spectra that we've just seen was going down to 4 unit cells.
I see.
Well, if you look at the spectra, this V-shaped behavior extends over larger energy ranges. So here it's zoomed in the 10 millivolt range, but also in the hundreds millivolt range is still there.
Are these spatially averaged, or do you see some? Is this a homogeneous behavior?
Yeah. So let's say we haven't studied the spatial behavior carefully enough to make a statement on that. But these are not spatially averaged. I think this is one point.
Mm-hmm.
There are some spatial variations, but they're not the main phenomenon here.
Mm.
And it's something that we haven't studied.
Thank you.
Thanks, Jean-Marc.
There is a question from Gertuvia.
Yeah, 45 degrees between domains. Yes.
Can I just ask it with the microphone?
No.
Yeah, hi. So thanks for the lecture. So in this interface, you always see the domain walls between the tetragonal domains in 45 degrees, and you lead to believe it's all in plane tetragonal domains. So now there was one point that maybe I missed, but you said that you see large anisotropy and resistance, and this is explained because of these 45 degree domain walls. like in the STO-LEO where you have with the Binsky squid, she shows how you have the modulated current. So you claim it's the same picture here, because you said something about DFT calculations to explain it, so I kind of missed the point there.
Okay, yeah, okay. Let me take a step back. So in the case of LEO STO, you have the two-dimensional electron system that is confined within the STO. So within the STO, the system experiences this spatial inhomogeneities associated with the domain walls, and then you have these more conducting lines along the domain walls.
Yes.
Here we have a system in which you have the STO, and on top of it you put an orthorhombic material that is conducting. Then, so what we're showing here is that the orthorhombic domains of the system have been locked locked with the tetragonal domains of the substrate.
I see. So okay, so saying you're not observing strictly the tetragonal domains of STO, but you're observing the domains of your layer, but they're just locked one another.
Yeah, exactly. So we are observing the action of these tetragonal domains on top of the structural domains of our.
And I see. And if you would have done a squint, do you imagine also having a modulated currents on these on the domain walls?
So Bina Kaliski has these samples, and hopefully we will. I'll be able to show you some.
I see. So actually, from work we've done with them on the ferroelectric STO with calcium and LAO interface, we also see this tendency for the 45-degree, but I guess it's a different reason there, because we at least speculate it has to do with the ferroelectric polarization.
I mean, that is another interesting point. So there are some indication that there is a polarization along these domain walls, and he may play a role in this influencing the properties of the conduction of these domains.
Yeah. Yeah.
But I would leave it as an open point.
Yeah, I see. Okay. So thank you.
Thank you.
Okay, while we're waiting for further questions, I may want to make a comment on a very general comment on your very first or second slide where you showed this phase diagram, correlations versus strength of spin orbit coupling. You made a mistake that we all do, that we are working with strong coupling spin orbit systems, and that's that you noted down that the strength of the spin orbit coupling scales as atomic number to the 4th power.
Yeah.
That's strictly true only for hydrogen-like atoms.
That's true. You're absolutely right. Absolutely. Yeah. So in reality, there is a screening of the potential done. Yeah, you're right. Thank you for pointing this out. I should have removed that. I was actually thinking this.
There is an old paper by Lev Landau on this, where he goes through the periodic table and shows that the exponent is somewhere between 2 and 3.
Yeah.
But nonetheless, the heavier, the higher the Z, the stronger.
You're right. Thanks for pointing it out. You know, when you consider the screening of the valence electrons of the nuclear potential, then it's far from being Z to the 4.
Yeah.
There was one more question
from Jean-Marc.
Yeah, Andrea, you showed that with slide you can induce these elastic waves in, I think it was lanthanum aluminate, and you showed that you can induce longitudinal waves and transverse waves. I was wondering, because if you have the 2 polarization, you could, I was wondering if it's possible to launch also coupled waves like surface acoustic wave or interface acoustic waves. Would there be a way to do this?
I think so. So I think with an opportune patterning of top electrodes that are kind of imparting some directionality to your waves to begin with, and some shaping of your electric fields, I think this will be possible. And I was actually thinking of your beautiful ideas on the surface acoustic waves in the ferroelectrics, and I think this would be quite interesting to try as a new way to approach the problem of a surface acoustic wave and their shaping in ferroelectrics. So ferroelectrics are on the menu. We have grown barium titanate in films, and we also have barium titanate exfoliated membranes that we want to look with this approach. Okay. So we would like to exactly test this type of ideas.
Okay. Thank you, Andrea.
Okay. There seem to be no further questions at this point. Okay, then, yeah.
I'm going to
Andrea,
remove the Z to the 4 from the slide before I send it to Mark.
Okay, thank you. Thank you for this very nice presentation. Thank you for all for participating. So we have one more lecture left in this school to this afternoon at 5 p.m. by Harold Wang. See you all back then. Bye-bye.
Thank you.